Now we're going to have two talks, one on aviation and power propulsion, and one on power generation. To start with, it's my great pleasure to invite Dr. Alan Epstein, Vice President of Technology and Environment from Pratt & Whitney. Dr. Epstein is responsible for setting the direction and coordinating technology across Pratt & Whitney. He also provides strategic leadership in reduction of environmental impact of Pratt & Whitney worldwide products and services. Prior to joining Pratt & Whitney, he was R.C. McLaren Professor of Aeronautics and Astronautics at MIT. He currently holds an appointment there as a Professor Emeritus, and he's a member of National Academy and Honorary Fellow of AIAA, a Fellow of ASME and Royal Aeronautical Society. He's also my doctoral father. I did my PhD with Alan, so it's my personal great pleasure to invite Alan back here to Zurich.
Thank you. It's always reassuring to see the student exceeding the professor. I have a generic title, but in fact it's very much in the flavor of the previous talk. Meetings like this are typically on technical details. And when I was a professor, I was concerned about technical details. I've been educated that money is actually important to a business. And I'd like to show how those come together in terms of trying to plot what the future might be. And we're assaulted in industry by buzzwords. Buzzwords are whatever the business magazines are publishing. Disruption, innovation, Factory 4.0, digital threads, it goes on. And I'm going to try to address some of those here. But let's distinguish between technologies and products. On the left is the first Pratt & Whitney engine, the WASP, in 1925. Air-cooled engine. It had essentially no features that hadn't been demonstrated in other air-cooled engines in the previous decade. But it put them together in what the Smithsonian called an unusually harmonious way. In other words, they all worked. And it really set the standard for piston engines for the rest of the aviation age until the jet engine came in. So it wasn't a disruptive technology, it was a disruptive product and replaced many of the water-cooled engines. This is Whittle's jet engine in 38 and von Ohnheinz in Germany. Those are disruptive technologies that basically disrupted the piston engine business over the following 10 and 15 years. Most recently, the Pratt & Whitney family of geared turbofans has some new technologies in it, but it's a disruptive product in that it forced the industry to come out with new products, the competitors to come out with new products that answered to this. And of course, what it's all about is trying to create value. In aviation, there's my customer's value, which would be the airline or the airplane manufacturer. And here are two airplanes, 707, the first successful commercial jet, and a newer one, the 787. If you're not an aviation person, they sort of look the same, looking from the top, just a couple. One has two, one has four engines. But one is 70% more efficient per passenger kilometer than the other. The result of enormous technology investments over 50 years. And new capacity. So there's a lot of capability in the fact that I live in Boston, I can fly Boston to Peking, Beijing, or Shanghai, now direct, nonstop, where we couldn't before. So that opens up new areas. And then the fuel economy of things like the geared turbofan is worth about $25 billion to the world's airlines in reduced cost over the next decade. So it's been very successful. But from the point of view of my management, they don't care about that stuff. They want to improve margins for their investors, or they want to enlarge the business. It's really no different than any other business. So let's first consider how peculiar the commercial airplane engine business and airplane engine business is. So consider it's an extremely long-term business. We talked about infrastructure, which is there for many decades. Aviation engines are also there for many decades. The J-57 started development in 1949. It went into service in '54. It's still in service 70 years later. It will be in service for another 10 or 20 years, generating revenue during that period. Another engine was the J-52, which became the JT-8D, originally for a missile in the '50s, then a fighter plane, then the 727s and MD-80s. There's still a couple of thousand of them flying many years later, generating revenue. In fact, close to 40 years after they were introduced, in the turn of the century, those particular engines were the largest revenue stream in commercial engine aviation. So these are very long-term investments if they're successful. If they're less successful, they disappear, and we pretend they weren't there to begin with. Engines, there are public list prices published by asset managers and leasing companies for these engines, and basically they're commodities sold per pound of thrust. $200 to $300 per pound of thrust is a typical price for an airline engine. We can go over why the curve looks like it does, but that's a constraint. Airplanes are sold per pound of capacity, gross takeoff weight, as certified. If you want an airplane with less gross takeoff weight than it can deliver, the airframer will sell that to you at a reduced price and give you a certificate that says you can only operate that as a reduced takeoff weight airplane, and we'll sell you engines at reduced takeoff thrust, certified for that reduced takeoff thrust. If a later purchaser wants to buy that airplane and increase the takeoff thrust or increase the gross weight, they actually have to go and pay the engine company and the airframer to do that. And in the old days, it was putting a plug in to tell the engine that it was now more beefy. These days, it's software download, but it's connecting value to money. Now, if I plot these two together, that is the vertical axis is the list price of the engines, the airplane list price is horizontal, and yes, they're both sold at discounts, but the ratios are about right. What you see is the engines are about 20%, 18 to 20% of the value of the airframe. That's a constraint, because what I find is my airframe customers don't want to pay me anymore for my engines. They're basically saying they're willing to let on the order of 20% of the value go to the propulsion provider. If they can negotiate me down to 18 or 17%, they got a great deal. If I can negotiate them up to 22%, I got a great deal. But that's the business part of it. It's a key point, because what it says is, as we develop new technologies, they can't add to the cost of the product. So for every new technology that adds cost, I need a technology that takes cost out, because I can't sell the engine for any larger fraction of the airplane. Now, for narrow-body airplanes, since the 727 in the early 60s, the cost of operating the airplane in corrected dollars has actually come back down by 40%. That's the value generated by the design technologies for the engine, airframe, avionics, as well as manufacturing technologies. Now, that's the good part. The bad part for manufacturers, the selling price hasn't budged. So it's much less expensive to operate for the airlines. We're not generating any more revenue for the manufacturers. What's going on? What's going on is, the airlines weren't generating large profits either for many decades. They were giving it away to their passengers, so airfares dropped by an order of magnitude since 1960. And so we took it out by growing the size of the market enormously, and it's continuing to grow at about 5% a year. But that still doesn't address my business concern of how do I increase the returns and the margins in what I do. And here's historically, say before 1990 certainly, the business selling commercial jet engines was about half the engines went as new engines on new airplanes, 45%, 10% were spares, and overhaul and selling spare parts was 45%. So it's about equal, installed engines on airplanes and overhaul. But the net income was much more profitable to overhaul and provide spares than it was to do installed engines. That was prior to, say, 1990. Now, it's changed quite a bit. We make no money selling engines. Actually, on a good year, we make no money selling engines. All of the net revenue comes from overhaul and spare parts, which has a profound effect on how you think about new engines. In the good old days, here's what an engine development looked like. If I had to go to my banker and borrow money to invest in the engine, I'd go and I'd ask for about $1 billion for small engine for engineering development over the course of 5 years. And then, because the first engines are usually very expensive to make, we haven't learned out how to do it, we're losing some money further on, but then we start making money both on engine sales, and then as the engines come back for spares, we make more and more. And you could argue over the shape of those curves. Some of them go up almost exponentially. Some of them abruptly die. That was the old days. Now it looks more like this, because we're not making money on selling the engines. We're putting billions of dollars into engineering development. We're putting billions of dollars into capital. We're putting billions of dollars into early sales concessions versus the manufacturing cost. We lose money for about 25 years. Now, I see our investor here has a very sick look on his face. For our newest engines, the official number from our CEO is we're down 11 billion. Right? But then it goes very positive indeed. So the investors really like the green, but not so pleased with the red. And what's been happening is the red's been getting bigger and deeper as the time's going on in the last 20 years. And people are starting to ask, do I really want to invest in this business? And how do I change this investment strategy? Because indeed, I bet even for the die-hard older academics here, if I gave you $11 billion to invest up front, you might be able to find better paybacks than 25 years. Now, so we're looking for things that are new. We're looking for things that are innovative. We're looking for disruption. But we also have to be mindful of evolution. So a technical meeting like this, we talk about technical stuff. And here's an excerpt from the Mechanical Engineering magazine in 1945 on the jet engine. And they talk about all the interesting things they have to work on: high-temperature alloys, high-speed bearings and bearing resonances, distortions due to temperature, compressor and turbine designs, aerodynamics, structures. Funny that those are all the things that we work on still today. And those are, to a large degree, how we've gotten the 50% improvement in engine fuel burn over this period. And historically, we know we're working to reduce fuel burn. The 707 was about 20% overall efficiency. The newest engines are a little over 40. And we think the ultimate is on the order of 60 or so. So there's as much headroom to improve engines as there has been in their total development. So that's one evolutionary factor, perhaps, although we may need innovation, certainly need innovation to get there. Here's a British magazine from 1911, and there's an article on the fitting of silencers to airplanes. And they state that they think that the racket doth prejudice the public against us. And I flew through Heathrow yesterday, and we know the They're still holding that grudge from 1911 in terms of the British aeropress. And so for the history of jet engines, we've worked hard to reduce the noise. And this happens to be Chicago O'Hare takeoff. But you see that from the 707, even to the very large airplanes, the 380 and the 777, the A320ceo. Now the A320neo, we've reduced the area on, these are 75 dBA contours, by about a factor of 10. So enormous progress. I was just talking to the noise group at O'Hare. They got 224,000 noise complaints in the last quarter of last year, because it's now all automated. So we still haven't quite solved that problem. You could ask from an engineering point of view, how quiet do you have to be? And we've done that calculation. If you can take 6 dBA off that class of airplanes, you can keep the 75 dB noise contours over the runway. Now, 6 dB, as you know, is a factor of 2 in noise. It's a very non-trivial number, which you'll probably never get from an existing design, but it's not the numbers I'm used to thinking about, 30, 40 dB. It's also, for the Neo, the engines are only a dB quieter than the airframe on takeoff. So you quiet the engines, you still have to work on the airframe, but that's not my problem. That's the airframers, guys. They will no longer be able to submarine behind the engine people on noise complaints. And indeed, in an evolutionary sense, at Pratt, we're working on advanced propulsors that have much lower noise and much lower fuel burn, suitable, say, for a 2030 airplane. There's one at a NASA rig, same one on a full-scale engine. Of course, again, the development for the technology has to precede the 5 years that we do the engine development on. One thing we don't talk about meetings like this are controls and accessories. This is you see the picture of the inside of a jet engine, and it's very familiar to you all with blades and combustors and discs and all that good stuff. But the outside of the engine is festooned with controls and accessories. 25 megawatt Neo engine is 40 centimeters in diameter. It weighs less than the accessories around it. And the costs are now starting to come comparable. These, by the way, aren't all the accessories, because many of them are put on with podding of the nacelle. And so we're now reaching the point where the tail is wagging the dog, and if we don't work on the controls and accessories, we won't realize the benefits from investing in traditional things like better compressors and turbines and combustors. So the enthusiasms of our time, I get clippings from our CFO and the chairman on what are we doing on the cloud, big data, digital twins, factory 4.0, out of manufacture, electric propulsion. And since they control the money, you actually have to answer them. So let's talk about the cloud in the sense of engine computational design tools, a topic that many in this audience are extremely expert in. 1950, that J57 was designed with slide rules and mechanical calculators. 1960, the J58, which is the engine on the SR-71, was still designed with slide rules, although we had tube computers then, which filled large spaces. Some of them we still have. Go forward a decade, and we had the IBM 360-65, which some of us went to school on, and that was used to design the first F-15, F-16 engines. By the middle 80s, we'd gone to a Cray, and that $32 million Cray was Pratt & Whitney Engineering's pride and joy. People just used to look and admire it, much less finagle how to get computer time on it. And that designed a much-endued, I left my cell phone over there. My iPhone has 100 times the computer power of the Cray XMP, by the way. It doesn't cost $32 million, although Apple's certainly making a fortune much greater than that than Cray ever did, so there's a message there perhaps. F-22 engine, the F-119, cranes weren't enough. We used 1,000 workstations networked together. That latest airplane is the F-135, F-35 engine, F-135. That was designed with cluster, and a cluster with tens of thousands of nodes in it, growing all the time, still growing all the time. What's next is the cloud. So we're actively looking at moving onto the cloud for as many of the calculations as we can for security purposes. Why do we want to do that? We're going to do that because in the midst of product development, if we run into as a professor, I'd call it a problem, but here I'll call it a challenge or an opportunity, right? We have 2,000 engineers working on this project. We have commitments to customers. We want to get it solved ASAP. We're willing to pay almost anything for computer time if the computer calculations will help us move forward. And so having that expandable capability in a big cloud, which means you need the codes that can do that as well, it has a lot to contribute. Now, this isn't designing the product. We make our money out of engine maintenance. So if we go back to that J57, the information for maintenance were handwritten logs. You move forward to the J58 on the SR-71, it had a digital and analog mission recorder that recorded 850 parameters. An astonishing thing for a development that started in 1958. However, back to the F-100, that was really mechanical. By the time we got to the 229, now we had a digital computer on board to record the diagnostic units. And these are different than the engine control computers. And that's because it's very hard to change engine control computer software because it's safety critical. It's much more economical to put it in a separate machine. The F-119 has 2, and the F-135 also has 2, and it has more computer power in the diagnostic units than it does in the engine control computers that run full state models of the engine all the time. And there's something called EFAST. EFAST is a box that now goes on commercial airplanes. It monitors thousands of engine parameters 10 times a second over the entire flight. And when the airplane lands, it has a cell phone on it. It calls home and downloads the data. Now, you don't do that on a military airplane because you want a secure link, you want to plug things in. But the point is, we're now bringing in an enormous amount of data compared to where we did. We monitor it in every flight. We're moving towards analytical certification. And the other part of the digital thread is measuring all of the parts as they're made and keeping track of which part is in which engine to know how to solve problems. So, Factory 4.0, what are we doing at Factory 4.0? Well, actually, Pratt & Whitney is a machine tool manufacturer from the 1850s who happened to have some extra machine tools and some empty factory space and agreed to invest in this airplane engine company if it took its name, also used its machine tools and space. That's how the name Pratt & Whitney came about. Pratt & Whitney still makes machine tools, but the company's split in 1930. Numerical machine started in the mid-50s, used on gas turbines. High isostatic pressing, which is the heart of disks in modern turbines, also 1950s. Numerical tape machines, late 60s, CNC tape machines, 5-axis mills in the early 90s. All of these are connected, whether the connection in the 50s was bringing tapes to the machine, now on a network. Vertical turning mills, additive manufacture came at the beginning of this decade for metals, earlier for plastics, and white light inspection. The point is, since we're extremely constrained in the selling price, we're extremely concerned in the manufacturing cost. And what we don't have generally are big conferences on technologies for manufacturing advanced jet engine parts. And the reason is that's too dear to share with people. We share it with partners, but because that's part of the heart of the technology. Now, you could argue that this is all evolutionary. Where does it can become disruptive? The aftermarket business is really important to us. If you have 3D printing, then you can make parts that look like other things. You also have white light inspection, which means you can very quickly determine accurately the shape of a part. And so this brings up a business risk to us. People counterfeiting parts, people making unauthorized parts, new people getting into the business and forcing price erosion. That would be disruption. One last topic. I am very concerned in my job about climate change and aviation's response to it. 98% of aviation CO2 comes from airliners above about 30 tons, call it 70 seats and above, roughly. That implies enormous powers and energy. So there's a lot of talk about electric propulsion. Will it be real? In order to be real, it has to be able to, A380 is 300 megawatts of takeoff power. It's a large power plant. It has more energy on board than a naval warship. So you need engineering solutions in that class. Let's say people come up with them. Whether they will or not is a different discussion. Here's the thermodynamic efficiency of aircraft engines at cruise. So this is the efficiency from the fuel in to the shaft that turns the propeller or fan. Conceptually, what could be replaced by a electric motor. Given the fact we know the fuel, we know the efficiency, we can calculate how much CO2 comes out, which is on the right, so that's CO2 per grams per kilowatt hour. The world's power grid is there. So in other words, the world's power grid is less efficient than the world's airplane engines. And that's because the best of airplane engines are more efficient than the best combined cycle power plants, that is a cruise. And the average aircraft engine is much better than the average power plant, cruise, even putting in currently where we are in renewables. So if you could make battery-powered airliners to the point of climate warming, you don't want to. If you had to, or if you could, then you'd need 23% more electricity, a boon to investors perhaps. Under current prices, that's about $1 trillion in gas-fueled power plants, 2 to 4 trillion in using renewables or distribution. And if that's energy, if you think of power, Atlanta needs about an $80 billion investment to meet the flights per hour through it. So it's a major change to the world's infrastructure should that happen. People talk turboelectric. You take a gas turbine, you put a generator, cabling, motor drives, whatever. I love this. UTC makes all of this stuff. And so it's even more stuff to sell to the airframer. The net efficiency in the future is probably about 90%. It's now about 80%, but people talk about going up to 80%. So up to 90%. So you'd lose 10% in propulsive efficiency. The weight ambitiously is about 3 times heavier than just the gas turbine. A 2x increase in cost, which presumably then gets as cost to the manufacturer. Turns out the electrical equipment costs the same per kilowatt as the gas turbine now. But people say it enables novel aircraft architectures. So going back to an investor, how much reduction in operating costs do I need for the investment to pay for itself? That is a 2x increase in the propulsion system cost to the airframer. The current discount rate, which is about 7% for airlines, it's a little over 40% at today's fuel price. Fuel goes up to $4 a gallon. It has to be about 18, 19%. Think of that as the engineering requirements, the financial requirements flow down to the engineering requirements to whether that innovation can do something. Last point is that's taking airliners doing airliners. I can't build flying cars now. One reason is I didn't have command and control, but you can see how autonomy solves that. The other is I didn't have dependable, low-cost propulsion. Gas turbines are by far dependable enough, but they never get down into this size range, being affordable. So electric propulsion there may indeed be the enabling technology for flying cars and taxis and such things. That would be disruptive to many industries. It's not disruptive to the gas turbine industry. It's an expansion of the industry in that sense. So let me conclude by saying airliner propulsion, it's pretty clear to me that gas turbines are going to dominate for the next several decades. They're the lowest cost, lowest CO2, lowest noise solution. Innovation is need for gas turbines all over the place. Improved materials, manufacture, perhaps more electric aircraft and engines, and disruption, certainly at the small end. Value creation in things like enabling flying taxis. So thank you.
Dr. Epstein is here for the panel this afternoon, but is there one question that somebody would like to pose? If not, there's an opportunity in the afternoon to ask a question. Thank you very much, Alan.